Saxon Math Course 3, we're looking at Lesson 15. We're going to talk about powers and roots. In this section, we're going to be talking about something that you've talked about before, that you know about, that you've seen. It is exponents, and we sometimes refer to an exponent as a power. So in this example here, you've got 5 to the second power, where 5 is considered the base and 2 is considered the exponent. Sometimes we'll use the term power to indicate the same thing as an exponent. So if I have 3 and a little 4 up here, this is 3 to the 4th power, and we know what it means. It means to multiply 3 4 times, or 4 3s multiplied together. And so the base here is 3, and the exponent, or the power, is 4. Here in example 1, we are asked to simplify each of these. And so in this case, we're actually supposed to do the math. So in example 1, part A, we're going to take 5 to the 4th power, and you know what that means. We're multiplying 5 by itself 4 times. And the easiest way for me to do that is to multiply 5 times 5 and get 25. And I happen to know that 25 times itself is 625. It's one of the ones that I've memorized. I would suggest that memorizing your perfect squares and some of these problems that'll come up, like 5 to the 4th power, that'll come up from time to time, or at least 25 to the 2nd power, that'll come up. I would suggest memorizing those so it makes your life easier. Of course, calculators exist. Of course, long multiplication exists. Let's talk about this next one. We're going to be multiplying 10 to the 4th power, so we're doing 10 times 10 times 10. The cool thing about multiplying by tens is we just get to add a 0 at the end for each of the tens there. So if I were to multiply 1 times 1 times 1 times 1, I get 1, and then I'm just going to add the 4 zeros right there. And so 10 to the 4th power is 10,000. In example 2, we are asked to prime factorize 72 using exponents. So 72, if I prime factorize it, it means I'm figuring out all of the values that multiply to give me 72. We talked about this earlier. So 9 times 8, I know is 72. Since neither of these are prime, I'm going to keep working. I can take 9 and break it down into 3 times 3. Since those are prime numbers, I'm going to put a little highlight on it to realize that I've done that line or that branch. And now I'm going to come back over to 8 and recognize that 8 can be written down as 2 times 4. These are two factors of 8. 2 times 4 gives me 8. Since 2 is prime, by the way, the only even prime is 2. Since 2 is prime, I'm going to highlight that. And then I'm going to break 4 down into 2 and 2. And therefore, everything, all of the branches have ended with these little highlights, and so I know that I'm done. So now 72 can be written in prime factorized form as 2 to the 3rd power, since I have 3 2's, and 3 to the 2nd power. So 72 prime factorized is 2 cubed times 3 squared. Here in example 3, we're given a word problem, and we're asked that the figure shown is a square floor tile that is 1 foot on each side. Find the area I don't even know what I'm reading. Find the area covered by the tile in square inches. Okay, now I know what I'm reading. Okay, fine. So here we are. We have this square floor tile, and we know that each side is 1 foot in length, or 12 inches. So if we consider that 12 inches on each side, if we thought about it, and let me see if I can find a gray pen here. If we thought about it, what we know is that if we were to split each side up into 12 pieces there and 12, I don't count these because I don't think that they're 12. I'm just trying to make it up. But if we were to split them up into 12 like that, 12 vertical lines and 12 horizontal lines to get, 12 by 12, we would have how many squares? That's what they're literally asking us. And so we're going to calculate that. We're going to answer that in the way that we know. We're going to multiply 12 times 12. 12 squared is another way of saying 12 times 12 is 144. So we would say 144 inches squared, or watch this confuses so many people, but I'm going to write it anyway because you're going to get used to it. You could have 104 inches with a little 2 up here, which means the same thing as inches squared there. So inches squared and inches to the second power. You're not actually putting 144 to the second power, okay? But this is just notation to say that inches squared can be written as inches squared with a little 2 there. Here in example 4, we're going to express an expression that looks kind of messy here with exponents. So we've got 2 and an x and an x and a y and a y and a y and a z. All of this is being multiplied together. So 2 we can leave by itself since there's no other number that we recognize that we can multiply that. But we've got 2 x's, even though I don't know what x is. I can look at these 2 x's and call that x squared. These 3 y's, since they're being multiplied, would be y to the third power, and z just has to hang out there by itself. So this is equivalent to the original one. We're still multiplying everything there. So here's a new concept we're going to talk about. It's the radical sign. The radical sign is the symbol that we use. It looks like division, but it's not. That didn't help. It's the symbol that we use to represent undoing something that is squared. So I can talk about the square root of 4. What I'm asking here is, I'm literally kind of asking a question when I see the square root of 4. And that question is, what number multiplied to itself will give me 4? Let's make itself one word. What number multiplied to itself will give me 4? And so with this question in mind is how I answer this. So the square root of 4 is that number, and that number is 2. Because 2 times 2 we know gives me 4. So since 2 squared equals 4, the square root of 4 equals 2. That's the process of thinking that we're using. So let's try another one. I can do the square root of 16 because I know that 4 squared is equal to 16. Therefore, the square root of 16 has to equal 4. Do a couple more. Square root of 25. Hopefully you got that. It's 5. Square root of 27. That's going to be a hard one. Actually, we don't have an answer for that is an integer. It would be a decimal number, but if you could look at this, you might even realize it'll be decimal 5 point blah, 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 blah. You can use a calculator to figure out what that would be. If we did the square root of 36, however, since 36 is a perfect square, this is also another reason why knowing your multiplication tables cold is so important. When you see 36, hopefully you remember that 6 times 6 is 36. Therefore, the square root of 36 is 6. And so we can go on and on like that with all of our perfect squares. What you see up here is that there's another use of the radical sign. Let me go back a bit. So we did the square root of 25, and so does your book. Square root of 25 is 5. We don't usually say this, but there's kind of like a little tiny understood 2 that goes here. We never write it because we call this the square root, so we know we're talking about 2 numbers that multiply to give me a particular number. However, when we get on to further problems, like when we think about taking different roots, we can have like different numbers here, in this case 3. So what is the third root of 125? Well, if you thought about 5 to the third power, when we did that problem earlier before, 5 to the fourth power gave us 625. Had you multiplied it like this, 5 times 5 times 5, and then the other 5, you would have seen midway to the answer that we would have gotten 25 times 5, which is going to give me 125. So I know that 5 to the third power is 125. With this knowledge, with this understanding in the back of our mind, when we see the third root of 125, there's a specific question that's being asked. That question is, what number multiplied to itself 3 times, that's kind of a weird way of saying it, equals 125. So what number do I multiply to itself 3 times? That sounds weird, but you get what I'm saying. 5 times 5 times 5. So if I have 3 of those numbers and I multiply it together, 3 of the same number multiplied together, which one of those gives me 125? And it's 5. And therefore, the third root of 125 is 5. Let me put my answer over here. So we realize that this symbol, the radical sign, is called just that, a radical sign. The number underneath it is called the radical. And I don't think they're calling it here anything, but in most textbooks, we know that these are called the index number. It's the index number. And so we can do wonderful problems understanding what's going on and what these symbols means. Let's try some examples. So let's look at this example 5. This is asking us what number when I multiply it by itself. So if I have two of the same number and I multiply it and I get 144, what must that number be? Hopefully you know that 12 times 12 is 144. So we know that that answer is 12. Here in part B, they're asking a bit different. They're saying, hey, if you take a number 3 times, so in a way n to the third power is equal to 27. That's what they're saying. Some number to the third power is 27. What is that number? Hopefully, if you thought about it just a bit, some number times itself is going to give me 27. What could that number be? That number is going to be 3, right? 3 times 3 is 9. 9 times 3 is 27. So what we learned from that little thought process is that the third root or the cube root, both are acceptable ways of saying this. The third root or the cube root of 27 is equal to 3. Example 6 has us considering the floor of a square room that is covered with square foot floor tiles. If there are 100 tiles cover the floor, how long is each side of the room? Well, they told us that the room was a square room. So if we have a room that is a perfect square and we know basically the area, we can use that information to figure out the side lengths because we know the area of a square is going to be side times side or side squared. Side squared in this case is equal to 100 square feet or 100 feet squared, right? And remember that feet squared, that 2 does not have to do with 100. It's just a way of writing units here. So S squared is equal to 100 feet squared. What is S? S is equal to the square root of 100. S has to equal 10 because we know that 10 times 10 is 100. So 10 feet would be the dimensions or the lengths of each side of this square room. So when we think about all these numbers that we can find the square root of, we are considering them perfect squares. So the first thing we're asked to do in example 7 is to name the first 3 counting numbers that are perfect squares. So we're thinking about counting numbers. 1 times 1 is 1, that is a perfect square. 2 times 2 is 4, that also is a perfect square. 3 times 3, 9, that's a perfect square. I honestly want you to know the first 20 perfect squares. Let's do it. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6, 36. 7 times 7, 49. 8 times 8, 64. 9 times 9, 81. 10 times 10, 100. Only 10 more to go. And then we have 121 for 11 squared. 144 for 12 squared. For 13 squared, we get 169. And relatedly, 14 squared, we get 196. For 15 squared, we get 225. 16 squared gives us 256. 17 squared, sometimes I get this wrong, gives us 289. 18 squared gives us 324. 19 squared is going to give us 81 or 61. And 20 squared gives us 400. I would like you to be familiar with these numbers. These numbers should always pique a little interest in you. You should be able to look at it and go, you're a perfect square. Only 20 numbers to think about, consider, and memorize. I think you should do it. Please do that. Okay, then there are positive square roots. So if we take the first 3 as the text asked us, we can figure out the positive square roots. So if I take the positive square root of 1, that's 1. The positive square root of 4, that's going to be 2. And the positive square root of 9, that looks not like a 9. Positive square root of 9, we get 3. That's it for this lesson. Go on to the practice set, do all of them, and you may do the odd ones in the written practice, making sure you read the even because you know that they can appear on your next test. Take care. Saxon Math, we're looking at lesson 16 in Saxon Math 3. We're going to talk about irrational numbers. Before we look at this example, let's talk a little bit about what an irrational number is. Remember, we had the family tree of numbers where you got real numbers as one of the branches, and then we've got rational numbers, numbers that can be written as a fraction. We talked about ratio, rational numbers, and then we have irrational numbers. And when we talk about these numbers as decimals, we know that rational numbers are repeating decimals, so 0.333 or 0.123, or numbers that terminate, decimals that terminate. So like, I don't know, 10.473. That's a rational number. These are all rationals. Irrational numbers are numbers that don't terminate and they don't repeat. They just go on forever and ever, like pi. But also there's a group of numbers that are going to be irrational, which is the square root of anything or the root of anything that doesn't like resolve into an integer. So if I have like the square root of 4, oh, let me not do that. If I have the square root of 41, 41 is not a perfect square. It's not. So I know that this has to be irrational. Square root of 7, not a perfect square, irrational. Square root of 100, oh, that's a perfect square. So that doesn't belong in this section. This is actually a rational number. Let's scoot you over here. Does that kind of make sense? Let's use this thought process to think about this next problem. So this next problem, example 1, asks us, which of these numbers is irrational? So the question is, do we have a perfect square? So square root, part A considers the square root of 0. What two numbers multiply to give me 0 when I multiply together? 0. So is this irrational? No, technically it's rational. So I'll put an X next to it because it's not what we want. Let's check out B. B, when I take the square root of 4, we all know this, we get 2. So this is not irrational as well. C, well, C is double 4. Maybe that, square root of 8. Is there a number that I can take that when I multiply that same number by itself, I get 8? Hopefully you're realizing that the answer is no. There is no integer value that's going to work that way. So this is the one. It is the irrational buddy. Let's see if D plays out with our understanding. The square root of 16, is that irrational? No. 4 times 4 is 16, and therefore the square root of 16 is rational. So I'm putting X's next to the rational numbers, and I'm putting a check next to that irrational one, because the square root of 8, in a sense, is not a thing. 8's not a perfect square. Here we have one of those problems where we get to arrange things in order. I'm going to try to do this a little bit quickly. The lowest number we have is 0, so I'm going to put our 0 there. The next number we have looks like maybe 1, but then we've got this fraction here. Square root of 5 could be something. Let me at least organize the numbers I know. So I know 0, I know 1 comes after 0, 1.2 definitely comes after 1, 2 comes after that, and 3 comes after that. I just have the square root of 5 to deal with, and I also have 5/9. As I look at it, 5/9 isn't that bad because 5/9 is a fraction. I know it's less than 1. 1 would be 9/9. So I'm going to put 5/9 here, and I'm going to feel pretty confident about that. The next one that I have to consider is the square root of 5. Now, I don't know much about this, and what I know is that if the square root of 1 is 1 and the square root of 2, oh, I don't know that one. Let me do one that I know. The square root of 4 is 2. Square root of 3, square root of 4, square root of 5. No. Oh, the next one is the square root of 9 is 3. Because I've got 1, 2, then 3 here, I know that this number, the square root of 5, has to be between 2 and 3. I'm going to say it again. Because I've got 1 and 2 and 3 here, by taking the square root of 1 and the square root of 4 and the square root of 9, when I take the square root of 5, I know it must be between 2 and 3. And with that understanding, I'm going to take that very value, and even though I don't know exactly what it is, I'm going to put it between 2 and 3. So that's how I'm going to organize my answer. My answer is 0, 5/9, 1, 1.2, 2, square root 5, and 3. So let's look at example 3. Here in example 3, the area of this square is 2 centimeters squared. What is the length of each side? This is kind of weird. I know that it should be a number. It's a square, right? And I know it should be a number that when I multiply that number by itself, I get 2. So whatever S is, it has to be, when I multiply S times S, it has to give me 2 centimeters squared for the area. So S squared is equal to 2. The hard thing is that there is no nice integer that works here. Of course, you can grab a calculator, and if you did, to figure out what number would I multiply twice to get 2, you would actually get 1.414 blah, blah, blah. I remember that just from doing math problems over the years. However, let's say you don't know that. If you don't know that, what you're going to do is say that S has to equal to the square root of 2 and leave your answer like that. With that in mind, you are ready for the practice set, and you're also ready for the written practice. Again, do all of the practice set. That's very important. And then you can move on to the written practice, doing the odds and checking in with the even ones, because you know you can be tested on them. Take it easy. Talk to you soon. Hello, Saxon Math. Course 3, we're looking at lesson 17, and we're going to do something kind of fun. We're going to do rounding and estimating. Sometimes it doesn't seem like rounding and estimating is hard. It's not, but we need to kind of make sure that we can think about rounding and estimating in a thoughtful, clear, and beneficial way. And so when we round, we are looking for numbers nearby that end sometimes in zeros or fives or ends in a convenient way so that we can multiply, add, subtract, divide, or whatever we need to do in order for us to expedite the computational process. So let's see some examples about this. Here in example 1, they're asking us to round this number. Hopefully you can read it. 1,481,362. And if you have this large number, it is important to know how to read them. Sometimes I get confused, but it's important to recognize that this whole section up here is the millions, and this is the thousands, and this is the hundreds, and you read them in groups of these of the commas. Anyway, they want us to round this number to the nearest 100,000. So I like to keep my eye on that particular place that we want to round to. So this is the number of concern. So what we do, we either want to have this number stay the same, or we're going to see if this number should be moved up. And the way that we determine that is by looking at the digit after that place. Since 8, it's a pretty big digit, it's greater than or equal to 5, we know that we're going to round up. We're not going to keep this 4 at the same place. So when we round, look at my wavy lines that I'm using, we're going to get 1,500,000 as our final answer. And so this is a good approximation according to what we were asked, right? We were asked to round it to the nearest 100,000. This is a good approximation of this value. Here in example 2, we're actually asked to round to 2 decimal places. So let's see what that means. When you look at the decimal, the numbers after it, we're going to call those decimal places. So 3 decimal places, sometimes you might talk about that as significant digits in chemistry or other sciences. Here we're going to refer to them as decimal places. So as I'm looking at this number, I'm like, oh, this is pi. Okay, so anyway, this is an approximation of pi to 1, 2, 3, 4, 5 decimal places, but we're going to round this to an approximation of pi down to 2 decimal places. So we're looking at these 2 decimal places here, and so actually we're really looking at the 4, and we're going to round it to 4. So the question is, are we going to have it as 3.14, or are we going to round up to 5? Because 4 can either go up or stay right where it is. Since 1 is lower than 5, we're not rounding it anywhere. We just go right here. We don't even go to the 5 or the 9. Since 1 is less than 5, we're going to leave the 4 exactly where she is. And so we've rounded this number to 2 decimal places. All right, so we've reached example 3, and we're going to be rounding each number to the nearest whole number. So if we have 13 and 5/12, it's kind of tricky to figure it out. Some kids actually think, I'm going to bring up this other one, part B. So this is A and this is B. Some kids mistakenly think that 13 and 5/12 can also be written like this. And I hope you're not one of those kids. And if you are, be disabused of that notion. You can't. These are not equivalent. To change this portion to a decimal, I've got to do some division, some long division. So here's what I do. I recognize that this is saying 5 is being divided by 12, and so I write 5 underneath the not the square root, but the division sign, we know that this is the dividend. I'm losing my words here. And 12 is the divisor. So I'm going to divide 12 into 5. And before you say I can't, I know you can't. That's why we're about to get decimals. So 5 going to 12, no can do. But 5 going to 50, absolutely. So 5 can go into 50, and it goes in there like 4 times, because 4 times 12 is 48. And I just keep moving and grooving until I get enough numbers that I think that I can make a good approximation of what's going on. Or I could just do it till I'm done. Let's see what happens. So 4, we get this 2, we put the 0 down, 12 goes into there 1 time. That happens. Then we get 8. We drop the 8 down. 12 goes into 80. Wow, how many times is 12 going to 80? A lot, like 6 times, because 6 times 12 is 72. And then I subtract, and off camera I'm getting an 8. Wait a minute, this seems like, did we do this before? Let me scooch it up a little bit. Let's see what we got. 8, drop it down, we get the 80. Yeah, we did. It's like deja vu. I guess it's going to be 6, and then 72, and then 6, and then 72. So you see we get this repeating thing here. So this number, 13 and 5/12, can be written as 13 point, check it out, 416 repeating. And this 13 and 512,000, yeah, I said that right, can be written like this. This is not the same thing, okay? So these are not equal. That's what I want to say. All right, great. So we didn't do what they asked us to do. They said round each number to the nearest whole number. So if we're talking about the nearest whole number, you know we're looking at 3. Go to the digit after it. Is 4 greater than or equal to 5? The answer is absolutely not. Shall we lift 13 above its 13ness? No. We're going to just say that this is just about 13. All right. So that's our answer there. Here, on the other hand, we are looking at the 3. And in this case, 5 does follow right after 3. And that tells me that I'm going to have to lift this up. So this is about 14. And that's how we do that. This next example, we're not going to really do because we don't share a classroom per se, but I would like you to think about it anyway. Example 4 says, estimate the length of one wall of your classroom in feet. And I'd also ask you to see if it's right. If you have a measuring utensil that can check, and right now your classroom is whatever room you are looking at right now. So if you're in your room, in your house, in your living room, dining room, if you're in your car, wherever you are watching the video, know that you can estimate that length of one side of that space and see if you did a good job. Ask somebody. All right, let's try the next example. Here in example 5, we've got Ivan who wants to tile the floor of a kitchen that is 12 feet long and 8 feet wide. The installed tile costs $7.89 per square foot. Ivan calculates that the cost of the tile for the floor will be about $315.60. Is Ivan's calculation reasonable? Well, let's help Ivan out a little bit. We see he's got a lot of space to tile. Let's take a visual here. And the square feet that he has here will be 8 by 12. And so when I multiply 8 by 12, I'm going to get a value, and then I can take that and multiply it by 7.89, and I'll get another value. That'll tell me how much each square foot costs. But let's go ahead and do a little bit of estimation, shall we? So when we multiply 8 times 12, we already know that was not hard. We get 96. That's a lot of tiles, and it's also really close to 100. So let's say we have about 100 tiles to buy, which will probably make sense because sometimes you break a tile in the process of installation. You might want to back up one, whatever. So let's say he's going for 100 tiles, and each tile is going to cost $7.89 per square foot. And what this 100 represents is our approximation of the square footage here. So that makes sense. If I take this number, 7.89, I'm looking at it, I want to multiply it by 100. I could do it, but I could also just look at this as 8. So basically that's like $8. So already you see that Ivan has really underestimated, because apparently the fancy tile he wants is going to cost about $800 to do the entire thing. So I'm going with his calculation is not just unreasonable, it's woefully unreasonable. So Richard is paid $11.85 per hour. How much money does he earn in a year? 52 weeks if he works 40 hours every week. Well, Richard's working really hard, and we want to make sure and do some quick math ourselves. $11.85. It's kind of hard. A clear answer would be to multiply. Approximate this to $12. 40 hours a week, we can multiply that by 40, and then we can multiply that by 50 because it's just easier. You know what I mean? Not having to do the 52. So 12 times 40 is going to give me about how much he makes per week. 12 times 40 is going to be 48 with a zero at the end, $480 a week. And then if he makes I could actually approximate this about 500, right? But I'm not going to. I don't want him to oversell himself. So then 50 weeks at making $400 a week is going to come to, there's two zeros there. 8 times 5 is 40. 5 times 4 is 20, 24. He's going to make about $24,000 for the year if he works that hard. So $11.85 per week, $24,000. It looks like that's exactly what they did as well here. All right, let's see if we got no more problems. We just have our practice set. You know what I want you to do, all of the practices, and I also want you to do the odd number written practice problems. And of course, read the even ones because they could be on your test. I'll talk to you soon, sweetie. Take care.